There are exactly three rules comets follow when they approach the sun. They heat up, they outgas, they fall apart. 3i Atlas is breaking all three, and astronomers in Spain, Thailand, and Norway just proved it wasn't an accident. Independent telescopes, different instruments, same impossible result. Instead of fragmenting into chaos, this interstellar visitor is organizing itself into perfect symmetry. A stacked shell halo, a twisting tail that defies physics, a core that should be vaporizing but refuses to collapse. The data is global. The confusion is universal. Natural objects don't stabilize under thermal stress. They disintegrate. So stay with me until the end, because what we're about to uncover will leave you wondering if natural is still the right word. You'll want to stay close as 3i Atlas continues its journey through our solar system and the data keeps rolling in. Subscribe and follow along, because every new observation brings us closer to understanding what we're actually looking at here. Now, let's dim the lights and dive into this cosmic mystery together. Something impossible is happening right now, and we have the receipts from 3 different continents. Astronomers in Spain aimed their telescopes at a speck of light hurtling through our solar system. They saw something strange. Astronomers in Thailand pointed their instruments at the same object. They saw the same strangeness. In Norway, researchers confirmed it again. This wasn't a technical glitch. This wasn't one miscalibrated sensor or a rookie astronomer misreading their data. This was consistent, repeated, and utterly wrong according to everything we know about how comets should behave. The object in question is called 3i Atlas. It's an interstellar comet, the third confirmed visitor from beyond our solar system. It was discovered in July 2025 by the Atlas Survey Telescope in Chile, and from the moment it entered our cosmic neighborhood, it started breaking the rules. Comets are supposed to be fragile. They're cosmic snowballs, loose aggregates of ice and dust held together by gravity. So weak, you could probably pull them apart with your bare hands if you could reach them. When they approach the sun, the heat should tear them to pieces. The solar wind should strip away their outer layers. They should become chaotic, messy, disorganized. They should fall apart. 3i Atlas is doing the opposite. Multiple independent observatories have now captured images of this thing, and what they're seeing defies our standard models of comet physics. Instead of disintegrating, the comet appears to be organizing itself. Instead of chaos, there's symmetry. Instead of a diffuse, expanding cloud of debris, there's structure. A perfectly symmetrical halo surrounds the nucleus. The core remains intact despite passing through temperatures that should vaporize and fragment it. The tail twists and contorts in ways that shouldn't be possible under the known dynamics of solar radiation, pressure, and outgassing. Let me paint you the picture of what we're actually seeing here. The stereo. A spacecraft positioned to monitor the solar wind pointed its wide-field imager at 3i Atlas between September 11th and September 25th, 2025. To see something so faint against the overwhelming brightness of the inner solar system, scientists used a technique called image stacking. They combined multiple exposures taken over days, adding them together to reveal faint objects that would be invisible in a single frame. When they did this, they expected to see what comets usually look like near the sun: a fuzzy blob, maybe a faint tail, signs of fragmentation or outburst activity. What they got instead was a bright, compact orb with an oddly stable appearance and a tail that seemed to maintain its structure across multiple observation periods. The Punch mission, another heliophysics spacecraft designed to study the solar wind and corona, captured 3i Atlas between September 20th and October 3rd. Same result: a point-like nucleus, a short tail, structural coherence where there should be dispersal and chaos. Then came the ground-based telescopes, Lowell Observatories discovery. telescope in Arizona captured optical images on October 31st. The ICQ Comet Observations Group, a collaborative network of amateur and professional astronomers, got their images on November 8th. These weren't fuzzy, ambiguous blobs. These were detailed morphological studies showing multiple jets emanating from the nucleus. Some of these jets pointed away from the sun, which is normal for comets. Others pointed toward the sun, which is decidedly not normal. There were reports of what's called an anti-tail, a structure extending from the comet in the direction opposite to where physics says it should go. Imagine water flowing uphill. Imagine smoke falling instead of rising. That's the kind of wrongness we're talking about here. Now, before we spiral into speculation, let's acknowledge the obvious question. Could this just be observational error? Could the symmetry and stability be artifacts of image processing, stacking techniques, or viewing geometry? Scientists are trained to be skeptical, especially of anomalies that seem to violate well-established physics. The answer is maybe, but probably not. The observations come from different instruments using different techniques at different locations, observing at different times. Image stacking can create artifacts. Background star subtraction can introduce errors. Cosmic ray hits can create false signals. But when you see the same features across multiple independent datasets, you start running out of excuses. The timeline tells a story that gets stranger the more you examine it. Discovery in July 2025. The comet races inbound toward the sun, approaching perihelion, the closest point in its orbit. This is when comets typically start showing their true nature. The heat intensifies. Ices sublimate. Jets erupt. Fragmentation begins. 3I Atlas passed perihelion and kept going. Post-perihelion observations showed continued activity. Jets, tail changes, structural oddities. But no disintegration. No breakup. No diffuse expanding debris cloud. The nucleus remained intact. The coma, that hazy atmosphere of gas and dust surrounding the nucleus, maintained a surprising degree of organization. So here's where we stand. We have a confirmed interstellar object, a visitor from another star system, behaving in ways that challenge our understanding of comet physics. We have global, multi-platform observational data confirming that the anomalies are real. We have scientists scratching their heads, trying to reconcile what they're seeing with what the textbooks say should happen. The stakes here are bigger than one weird comet. If 3I Atlas is genuinely defying the standard model of comet behavior, then either our models are incomplete, or this object is fundamentally different from anything we've studied before. Maybe interstellar comets are built differently than solar system comets. Maybe the conditions under which they form produce structures that are more cohesive, more resistant to solar heating, more stable under extreme conditions. Or maybe, and this is where things get uncomfortable, we're looking at something that isn't entirely natural. I'm going to walk you through the data. I'm going to show you what we know, what we don't know, and what the various explanations might be, from the mundane to the extraordinary. By the end of this, you'll have seen the observations, the physics, the mainstream science, and the speculative theories that are starting to circulate in corners of the astronomical community. And then you'll have to decide for yourself. Is 3I Atlas just a really weird comet from another star system? Or is it something else entirely? Before we dive into the weird, we need to establish the normal. What do we actually know about 3I Atlas? What are the confirmed facts, the measured parameters, the baseline observations that any discussion has to start from? The discovery came from the ATLAS survey, the Asteroid Terrestrial Impact Last Alert System, operating from Chile in July 2025. ATLAS is designed to scan the sky looking for near-Earth objects, asteroids, and comets that might pose a collision risk. It's automated, systematic, and very good at finding faint moving objects against the background stars. When Atlas flagged 3I Atlas, astronomers quickly realized they weren't looking at just another solar system comet. The orbital parameters were wrong. The trajectory was hyperbolic, meaning this thing wasn't bound to the sun. It was passing through, a visitor from interstellar space. This made it only the third confirmed interstellar object ever detected. The first was Oumuamua, that cigar-shaped enigma that passed through in 2017 and sparked endless debates about whether it could be artificial. The second was 2I/Borisov, discovered in 2019, which looked and behaved exactly like a normal comet, much to everyone's relief. 3I Atlas is now the third, and it's bringing the weird back. Let's talk about size. The Hubble Space Telescope, still operational and still delivering crucial data decades after its launch, turned its instruments toward 3I Atlas to try to measure the nucleus. Comet nuclei are notoriously difficult to measure directly because they're tiny and surrounded by a bright coma of gas and dust that outshines them. Hubble's data suggests the nucleus diameter has an upper limit of about 5.6 kilometers. That's the maximum it could be. It might be much smaller, possibly as small as 440 meters across. That's a huge range of uncertainty, but it tells us we're dealing with something between the size of a large mountain and a small city. Multiple observatories coordinated to study this thing as it approached the sun. Ground-based telescopes in Spain, Thailand, Norway, the United States. Space telescopes, including Hubble and the James Webb Space Telescope. Heliophysics spacecraft designed to study the solar wind and corona. Even some planetary orbiters with wide field cameras pointed at 3I Atlas when their orbits allowed. This wasn't a casual observation campaign. This was a coordinated international effort to squeeze every possible bit of data out of this rare opportunity. Now let's talk about what comets are supposed to do, so you understand why 3I Atlas is so strange. Comets are sometimes called dirty snowballs. They're mixtures of water ice, frozen carbon dioxide, frozen carbon monoxide, methane, ammonia, and dust grains, all jumbled together in a loose aggregate. When a comet is far from the sun, out beyond the orbit of Jupiter, it's cold and inert. As it falls inward toward the inner solar system, solar heating begins to warm the surface. Ices sublimate, going directly from solid to gas without melting. This outgassing creates the coma, a temporary atmosphere around the nucleus. The solar wind, a stream of charged particles flowing outward from the sun, pushes the gas away, creating the characteristic tail. Solar radiation pressure pushes dust particles away, sometimes creating a separate dust tail. Jets erupt from active vents on the nucleus where sublimation is particularly intense. The whole process is chaotic. Comets tumble. They fragment. They have outbursts. They sometimes split into multiple pieces. They're fragile, messy, and unpredictable. 3I Atlas does some of this. It has a coma. It has tails. It shows jet activity. But it's doing it all with a stability and symmetry that's hard to explain. Spectroscopy gives us the chemical fingerprint of the coma. The James Webb Space Telescope, with its powerful infrared capabilities, observed 3I Atlas and identified the dominant volatile in the coma as carbon dioxide. Not water. Carbon dioxide. Water was present, along with carbon monoxide, dust, and water ice grains. But the ratio of carbon dioxide to water was unusually high, among the highest ever measured in a comet. This tells us something important about where 3I Atlas formed. Carbon dioxide ice is more volatile than water ice at large distances from a star. A comet with this much carbon dioxide probably formed in a colder region of its original protoplanetary disk, or perhaps in a system with different chemical abundances than our own. The Neil Gehrels Swift Observatory, an ultraviolet space telescope, detected emission from hydroxyl radicals at about 3.5 astronomical units from the sun. Hydroxyl is a byproduct of water sublimation. This detection confirmed that 3I Atlas was actively sublimating water ice, even at relatively large distances from the Sun, farther out than most solar system comets would start showing significant water activity. That's unusual, but not unheard of. It suggests the comet has a lot of accessible ice near its surface. Photometric observations tracking the brightness of 3I Atlas as it approached the Sun showed that dust production scaled with distance, roughly following a power law. The brightness increased as the comet got closer to the Sun, consistent with increased sublimation and dust ejection driven by solar heating. The exponent of the power law, about -1.8, is within the range seen in normal solar system comets. So in terms of activity level, 3I Atlas wasn't doing anything crazy. It was outgassing and producing dust at rates comparable to other comets at similar distances. But here's what we don't know, and these unknowns are critical. We don't know the exact mass of the nucleus. We don't know its rotation period or spin axis orientation. We don't have detailed maps of where the active regions are on the surface. We don't know the internal structure. Is it a solid chunk of ice and rock? Is it a loosely bound rubble pile? Is it layered with different compositions at different depths? We don't know the porosity, the amount of empty space between grains. We don't know the mechanical strength, how much stress it can withstand before breaking apart. All of these unknowns matter because they determine how the comet responds to solar heating and tidal forces. A solid, dense nucleus would behave very differently from a fluffy, porous one. A rapidly rotating comet might shed material more easily than a slowly rotating one. Without this information, we're trying to explain the observations with incomplete knowledge of what we're actually looking at. So that's the baseline. 3I Atlas is a confirmed interstellar comet with a carbon dioxide-rich coma, active water sublimation, dust production consistent with normal comets, and a nucleus somewhere between 440 meters and 5.6 kilometers across. It behaves like a comet in most respects, but in the details, in the morphology and structure and stability, something is off. And that's where the mystery begins. Now we get into the details that are keeping astronomers up at night. Forget the big picture for a moment. Zoom in. Look at the structure. Look at what the images are actually showing us. Because this is where 3I Atlas stops being merely interesting and starts being deeply problematic for our standard models. The stereo. A spacecraft isn't designed to study comets. It's a solar observatory, positioned to monitor the solar wind and coronal mass ejections. But its heliospheric imager, the HI-1 instrument, has a wide field of view that sometimes catches comets passing through the inner solar system. To spot something as faint as 3I Atlas against the bright background, scientists used image stacking. They took frames captured between September 11th and September 25th, 2025, and digitally combined them. Think of it like a long exposure photograph. Faint signals that are barely visible in a single frame become clear when you add many frames together. What emerged from that stacked image was unexpected. A bright fuzzy orb, a tail or coma structure, but also a compactness, a coherence that stacking usually washes out. When you stack images of a fragmenting comet, you get a smeared, elongated mess because the pieces are moving apart over time. 3I Atlas appeared as a distinct object with maintained structure across the observation period. The Punch mission saw similar features. Punch stands for polarimeter to unify the corona and heliosphere, another wide-field solar observatory. Between September 20th and October 3rd, Punch captured 3I Atlas, showing a point-like nucleus and a short tail. Again, stability where you'd expect chaos. Then came the high-resolution observations from ground-based telescopes. The Discovery Telescope at Lowell Observatory captured optical images on October 31st. These were post-perihelion observations, meaning 3I Atlas had already survived its closest approach to the Sun and was heading back outward. what the images showed was a complex jet structure. Multiple jets, not just one or two. Some jets pointed away from the sun, which is normal. Sublimating ice produces gas and dust that gets pushed away by solar radiation pressure. But other jets appeared to point toward the sun. That's wrong. That violates the basic physics of how comets work. The ICQ Comet Observations Group on November 8th captured similar features: multiple jets, anti-solar jets, and something called an anti-tail. An anti-tail is a geometrical effect that can happen when you're viewing a comet from a particular angle, and dust particles in the orbital plane create the illusion of a tail pointing toward the sun. But 3I Atlas's anti-tail seemed more substantial than a simple geometrical illusion. There appeared to be actual material, actual structure extending sunward. One recent preprint, a preliminary scientific paper not yet peer-reviewed, suggested a possible explanation. Large ice grains, not the fine dust typically seen in comet comas, but millimeter or centimeter scale chunks of ice. These larger grains would sublimate more slowly than fine dust. They could survive closer to the sun before completely evaporating. If these grains were preferentially ejected toward the sun due to anisotropic outgassing, jets firing more strongly on one side of the nucleus than the other, you might get a sunward extension of the coma, a snowline effect where larger icy chunks create a stable structure pointing the wrong direction. That's a plausible physical explanation. But it requires some very specific conditions. The nucleus would need to be ejecting unusually large ice grains. The outgassing would need to be highly directional. And the grains would need to be cohesive enough to survive the journey sunward without immediately disintegrating. Here's what's really bothering scientists. Despite all this jet activity, despite passing through perihelion, where solar heating should be at maximum intensity, 3I Atlas shows no signs of fragmentation. Comets break apart all the time. Some split into 2 or 3 large pieces. Some shatter into clouds of debris. Some undergo catastrophic disruption and just vanish, their material dispersed into space. 3I Atlas remained intact. The nucleus held together. The core stayed organized. Multiple independent observers confirmed these features. That's crucial. When you're dealing with something weird, you always have to worry about observer bias, equipment malfunction, or processing errors. But when observers in Spain see the same thing as observers in Thailand and Norway, when space-based instruments see the same thing as ground-based telescopes, when heliophysics missions see the same thing as optical surveys, the odds that it's all just artifacts drop dramatically. So we have cross-confirmed observations of structural stability, symmetrical halo, like features in stacked images, complex jet patterns including anti-solar jets, anti-tail structures, and a nucleus that refuses to fall apart despite being subjected to conditions that should tear it to pieces. The question becomes, are these features explicable through unusual but natural dust and gas dynamics, unusual viewing geometry, unusual coma composition, or is there something fundamentally different about the physical structure of this nucleus? Is the material more cohesive than typical comet material? Is the internal structure more organized, more mechanically strong? Is there some process, some mechanism we don't understand that's allowing this thing to maintain its integrity under extreme stress? The morphology is strange. The data is consistent across multiple platforms, and the standard comet models are struggling to keep up. Morphology alone doesn't tell us what's inside. It doesn't tell us why this thing is so stable, but it tells us something is different, and that difference matters. If you want to understand why something behaves the way it does, you need to know what it's made of. 3I Atlas isn't just throwing us morphological curveballs. The chemistry is weird too. And that chemistry might be the key to explaining at least some of the anomalies, or it might just deepen the mystery. The headline result from the James Webb Space Telescope's infrared spectroscopy is this. The coma of 3I Atlas is dominated by carbon dioxide, not water, carbon dioxide. Now, all comets contain some carbon dioxide. It's a common volatile in the outer solar system. But the ratio matters. Most solar system comets are water-ice dominated. The carbon dioxide to water ratio in typical comets is low. 3I Atlas flips that script. Its carbon dioxide to water ratio is among the highest ever measured in a comet. That single fact tells us this object formed under very different conditions than most solar system comets. Carbon dioxide ice sublimates at lower temperatures than water ice. Far from the sun, where temperatures are extremely cold, carbon dioxide ice is stable, while water ice requires even colder conditions or protection from direct solar heating. A comet with this much carbon dioxide probably formed farther out in its original protoplanetary disk than water-rich comets. Or it formed in a system with different chemical abundances, different ratios of elements and molecules than our own solar system. Maybe the star it formed around had lower metallicity, fewer heavy elements. Maybe the disk was colder. Maybe the formation process was different. But 3I Atlas also has water. The Neil Gehrels Swift Observatory detected hydroxyl emission, a tracer of water sublimation, at about 3.5 astronomical units from the Sun. That's relatively far out. Most comets don't start showing strong water activity until they're closer to 2 astronomical units or less. 3I Atlas was actively sublimating water ice while still in the outer solar system. That suggests the water ice is easily accessible, not deeply buried under layers of refractory dust or less volatile ices. The surface, or at least parts of the surface, must be rich in water ice that's exposed to sunlight and heating up enough to sublimate even at large distances. So we have a paradox. High carbon dioxide, which suggests formation in a cold, distant environment, but also active water sublimation at large heliocentric distances, which suggests accessible surface ice. How do you reconcile that? Maybe the nucleus is layered. Maybe there's a carbon dioxide-rich core surrounded by a water ice-rich mantle. Or maybe the surface is heterogeneous, patchy, with some regions rich in carbon dioxide and others rich in water. Spectroscopy also revealed the presence of dust and water ice grains in the coma, not just gas, solid particles. Some of these particles appear to be relatively large, not the fine micron-scale dust typical of most comet comas. Large icy grains, possibly millimeter scale or larger. These grains would sublimate more slowly than fine dust. They could persist in the coma for longer periods. They could travel farther from the nucleus before completely evaporating. And they might contribute to the structural stability of the coma, creating a longer-lived, more organized appearance. Photometric data tracking brightness as a function of distance showed that dust production increased as the comet approached the sun, following a power law with an exponent of about -1.8. That's consistent with volatile-driven outgassing, probably carbon dioxide, ramping up as solar heating intensifies. But it's not outside the range of normal comet behavior. So, while the composition is unusual, the activity level is not extraordinary. 3I Atlas isn't producing vastly more dust or gas than other comets at similar distances. It's just producing it from a different chemical mixture. Here's where composition might explain some of the anomalies. A carbon dioxide and carbon monoxide, rich nucleus with large icy dust grains, could behave differently under solar heating than a water ice-dominated comet with fine dust. Carbon dioxide sublimation is more vigorous at lower temperatures, so outgassing could start earlier and be more sustained. Large grains take longer to heat up and longer to sublimate, so dust ejection might be slower and more prolonged. Anisotropic outgassing, jets firing preferentially from certain regions of the nucleus, could be more pronounced if the surface is compositionally heterogeneous. All of that could, in principle, explain the observed morphology. The symmetry might not be perfect symmetry, but rather a quasi-stable coma structure, maintained by slow, sustained outgassing of large grains. The anti-solar jets might be large icy chunks ejected in unusual directions due to localized active regions. The stability of the nucleus might reflect a composition that's more cohesive, more resistant to thermal stress and fragmentation than typical solar system comet material. But here's the problem. Composition gives us clues, not certainties. We don't have in situ measurements. We haven't landed a probe on 3I Atlas. We haven't drilled into the nucleus or measured the mechanical properties of the material. We don't know the porosity, the internal structure, the grain bonding mechanisms. We're inferring chemistry from remote spectroscopy, which is powerful but indirect. We can see what molecules are sublimating off the surface, but we can't see what's underneath. A comet, even one with unusual composition, should still lose mass. It should still shed material. It should still show signs of erosion, outgassing-driven changes to its surface. Maybe fragmentation if the structure is weak. 3I Atlas is doing all of that, but with a coherence that's hard to reconcile with our models. Composition might be part of the answer, but it's probably not the whole answer. Maybe 3I Atlas formed under extremely unusual conditions. Low metallicity environment, different radiation field, different disk chemistry. Maybe it's a 1 in a million natural object, the cosmic equivalent of a lottery winner, with just the right mixture of volatiles and dust grains and structural properties to survive close solar passage intact. That's possible. The universe is vast. Rare events happen. Or maybe we're missing something. Maybe there's a physical mechanism, a process we don't fully understand, that operates in interstellar comets. Maybe the long journey through interstellar space, exposure to cosmic rays, bombardment by interstellar gas and dust, somehow alters the material properties, making it more compact, more cohesive, more stable. The chemistry is weird. It's weird enough to make you wonder, but it doesn't answer all the questions. It raises new ones. Science proceeds by consensus, built on evidence. The consensus on 3I Atlas, according to public statements from NASA and mainstream astronomers, is clear. It looks like a comet. It behaves like a comet. The activity, the coma, the tails, the outgassing, all consistent with a volatile, rich interstellar comet entering the inner solar system. There is no verified evidence of artificial origin. The anomalies, while interesting, are probably explicable through unusual composition, dust grain properties, and viewing geometry. Case closed, move along, nothing to see here, except a growing number of observers, some professional astronomers and many informed amateurs, are pushing back. They're arguing that the symmetry, the stability, the morphological features strain the limits of natural comet physics. They're saying the textbook explanations don't quite fit, and they're asking uncomfortable questions. Let's be clear about what's mainstream and what's fringe. The mainstream position is cautious and conservative. Yes, 3I Atlas has unusual features. Yes, the composition is carbon dioxide rich, which is rare. Yes, the morphology shows unexpected symmetry and stability. But comets are variable. Interstellar objects are poorly understood. We've only observed 3 of them. We don't have a large sample size. Declaring that 3I Atlas violates comet physics based on limited data would be premature. The prudent approach is to collect more observations, refine the models, and see if natural explanations can account for what we're seeing. That's the responsible scientific position. But it's also a position that can sometimes be slow to recognize genuinely anomalous phenomena. History is full of examples where the mainstream consensus initially dismissed observations that later turned out to be revolutionary. Continental drift, neutron stars, exoplanets, black holes. all of these ideas faced skepticism before the evidence became overwhelming. So what are the minority voices saying? They're pointing to specific features that don't fit easily into standard models. The anti-tail, which seems more substantial than a simple geometrical effect. The anti-solar jets, which require very specific and unusual conditions to explain. The lack of fragmentation, which is surprising given the thermal and tidal stresses near perihelion. The symmetrical halo in stacked images, which could be an artifact, but could also indicate real structural organization. They're arguing that while any one of these features might be explicable, the combination of all of them simultaneously is hard to reconcile with natural comet behavior. Some go further. A few vocal commentators, mostly outside mainstream astronomy, have floated the idea that 3I Atlas might not be entirely natural. They're invoking the same kind of speculation that surrounded Oumuamua. Could it be an engineered object? A probe from another civilization? A hull-like structure designed to withstand interstellar travel? Let's be absolutely clear. There is no evidence supporting this hypothesis. None. The spectroscopy shows volatiles, dust, ice, all consistent with a comet. The activity shows outgassing driven by solar heating, exactly what you'd expect from sublimating ices. There are no radio signals, no anomalous acceleration that can't be explained by outgassing, no optical signatures of artificial materials. The technosignature hypothesis is speculative in the extreme, bordering on science fiction, but it's worth understanding why some people find it compelling. Oumuamua had a weird acceleration that couldn't easily be explained by outgassing, and it had an unusual elongated shape. Those features, combined with its interstellar origin, sparked speculation about artificial origin. 3I Atlas doesn't have those features. It has different features, unusual stability and symmetry, and for some, that's enough to trigger the same kind of what-if thinking. The problem with technosignature speculation is that it's unfalsifiable without extraordinary evidence. You can always claim that sufficiently advanced technology would be indistinguishable from natural phenomena. You can always argue that our inability to explain something with current models doesn't mean it's artificial, but it doesn't rule it out either. That's bad epistemology. The burden of proof is on the claimant. Extraordinary claims require extraordinary evidence, and the evidence for artificial origin is currently zero. What about more plausible but still speculative hypotheses? Maybe 3I Atlas is a remnant of a low metallicity protoplanetary disk with dust grains and ice formations unlike anything in our solar system. Maybe the dust grains are unusually large, millimeter or centimeter scale chunks that create a stable, long-lived coma. Maybe dust cohesion, driven by electrostatic forces or chemical bonding, makes the material more resistant to fragmentation. Maybe slow sublimation, combined with large grain size, causes a kind of self-organizing structure, where the coma naturally settles into a quasi-symmetric configuration under the influence of solar wind pressure. These are thought experiments, not proven theories. But they're grounded in known physics. They're asking whether extreme but natural conditions could produce the observed features, and they're illustrating how little we actually understand about the diversity of small body compositions and behaviors. There's also the issue of observational bias and processing artifacts. Image stacking can create artificial symmetry. Background subtraction can introduce errors. Cosmic ray hits can mimic point sources or linear features. Viewing geometry matters enormously. Depending on the angle, a chaotic coma can look organized, and a tumbling nucleus can appear stable. Scientists are well aware of these issues. They apply corrections. They cross-check with multiple instruments. But perfect correction is impossible. Some residual uncertainty always remains. So where does that leave us? The mainstream consensus is natural comet. Unusual, but explicable. The minority position is natural comet, but pushing the boundaries of what we thought was possible, requiring new physics, or at least revised models. The fringe position is maybe not natural at all, though this lacks supporting evidence. The honest answer is, we don't fully know. We have data gaps. We lack in situ measurements. We don't have detailed knowledge of the nucleus structure, rotation, internal composition, mechanical properties. We're making inferences from remote observations, which are powerful, but limited. Even the natural origin advocates admit uncertainty. That uncertainty is what keeps this interesting. That uncertainty is what keeps people watching. Strip away the speculation and the fringe theories for a moment. Even if 3I Atlas turns out to be entirely natural, even if every anomaly has a prosaic explanation, this object matters. It matters because it's pushing the boundaries of comet science. It matters because it's showing us that interstellar objects can be fundamentally different from their solar system cousins. And it matters because it's forcing us to question assumptions we thought were settled. 3I Atlas is a confirmed interstellar object with active coma, dust tails, jet activity, and volatile-driven outgassing. It's not inert like Oumuamua appeared to be in most observations. It's not boringly normal like 2I/Borisov. It's somewhere in between, displaying comet-like behavior, but with features that challenge standard models. That makes it a Rosetta Stone for understanding the diversity of small bodies in the galaxy. The carbon dioxide-dominated composition tells us something profound about where this object came from. It didn't form in our solar system. It formed around another star, in a protoplanetary disk with different chemistry, different temperature gradients, different volatile inventories. The high carbon dioxide to water ratio suggests formation in a colder region or a chemically distinct environment. Maybe the parent star was lower mass, with a cooler disk. Maybe the disk had lower metallicity, fewer heavy elements, and different ice condensation zones. Maybe 3I Atlas formed early in its system's history, when conditions were more volatile rich. This diversity matters because it tests the universality of comet formation theories. Are comets everywhere made the same way? Do they all follow the same compositional patterns? Or is there a wide range of possible comet chemistries, depending on the host star, the disk properties, the formation location? 3I Atlas suggests the latter. It suggests that interstellar comets could be chemically and structurally much more diverse than what we see in our own solar system. That has implications for models of planetary system formation, volatile delivery to planets, and the chemical evolution of disks. Consider what this means for our understanding of how planetary systems develop. We've always assumed that comets and other star systems would be roughly similar to ours. Water ice, some carbon dioxide, some carbon monoxide, dust grains, maybe some organic compounds. We base this assumption on the idea that protoplanetary disks follow universal physical laws. Temperature decreases with distance from the star. Different volatiles condense at different temperatures. You get an ice line where water freezes. Farther out, where carbon dioxide and carbon monoxide freeze, and so on. Simple, predictable, universal. 3I Atlas is telling us that reality is more complicated. The chemical makeup of a protoplanetary disk depends on the composition of the molecular cloud it formed from. It depends on the mass and luminosity of the star. It depends on the disk's age, its density structure, its exposure to nearby stellar radiation. Two disks around two different stars might produce very different populations of comets, even if the basic physics is the same. That means we can't just extrapolate from our solar system to the rest of the galaxy. We need to expect variety, deviation, surprises. The morphological anomalies, the stability and symmetry, also matter for comet physics. If these features are real and not artifacts, they're telling us that our standard dust grain size distributions, cohesion models, thermal evolution calculations, and outgassing dynamics may not capture the full range of possible behaviors. Maybe comets can have large grain sizes that we rarely see in solar system objects. Maybe dust cohesion can be much stronger under certain chemical conditions. Maybe slow sublimation and sustained outgassing can create quasi-stable coma structures that persist longer than our models predict. These aren't revolutionary overturns of physics. They're refinements, expansions of the parameter space we need to consider. But they're important refinements. They mean that when we observe future interstellar objects, we can't just assume they'll behave like solar system comets. We need to be prepared for surprises. Think about what happens when you build a model. You make assumptions. You simplify. You focus on what you think are the most important parameters and ignore what seems like noise or edge cases. That's necessary. You can't model everything, but sometimes the edge cases turn out to be more important than you thought. Sometimes the noise is signal. 3i Atlas might be showing us that our comet models have been tuned too narrowly to solar system examples. We've been studying the local population and assuming it's representative. Maybe it's not. The observational campaign around 3i Atlas also demonstrates the value of multi-platform, coordinated observation strategies. Ground telescopes provided high-resolution morphological data. Space telescopes provided spectroscopy and photometry. Heliophysics missions provided wide-field context and near-Sun observations. Amateur observers contributed additional data points and rapid follow-up. This kind of coordinated effort, spanning multiple countries and multiple types of instruments, is essential for studying rare, transient phenomena like interstellar visitors. Each platform brings unique capabilities. Ground telescopes can achieve high spatial resolution, resolving fine details in the coma and jets. Space telescopes, above the atmosphere, can observe in ultraviolet and infrared wavelengths that are blocked or distorted by Earth's atmosphere. Heliophysics missions can track objects close to the Sun, where ground-based telescopes struggle with the glare. Amateur observers, with their flexibility and geographic distribution, can provide continuous monitoring and catch transient events that professional surveys might miss. The synergy matters. No single instrument can give you the complete picture, but together, they can. Future survey telescopes, like the Vera C. Rubin Observatory, once it's fully operational, will detect many more interstellar objects, maybe dozens per year. 3i Atlas is showing us that we need to be ready with rapid response protocols, pre-planned observation strategies, and the capability to mobilize diverse resources quickly. We might only have weeks or months to study these objects before they leave the inner solar system and become too faint to observe. Rubin Observatory, with its wide field camera and rapid cadence surveying, is designed to catch moving objects. It will scan the entire visible sky every few nights, identifying anything that changes position. That includes asteroids, comets, and hopefully many interstellar visitors. But detection is just the first step. Once you find an interstellar object, you need to mobilize follow-up observations immediately. You need spectroscopy to determine composition. You need photometry to track brightness and activity. You need high-resolution imaging to study morphology. You need coordinated observations from multiple sites to get continuous coverage. All of that requires planning, coordination, and resources. 3i Atlas is the test case, showing us what works and what needs improvement. There's also a speculative but tantalizing thought worth entertaining. If some interstellar objects are physically more robust than expected, if they can survive close stellar passages without disintegrating, could they serve as natural vehicles for transporting complex chemistry or even microbial life across interstellar distances? This is the Panspermia hypothesis. The idea that life might spread between star systems via comets and asteroids. It's speculative. We have no evidence that 3i Atlas carries life, or even complex organic molecules beyond the simple volatiles detected spectroscopically. But if interstellar comets are more durable than we thought, the possibility becomes slightly less implausible. Panspermia has always faced a timing problem. Interstellar space is harsh. Cosmic rays, ultraviolet radiation from stars, the vacuum of space, extreme cold. Any organic molecules or microbial life on the surface of a comet would be sterilized within thousands to millions of years. But if the interior is protected, if the object is large enough and dense enough that radiation can't penetrate to the core, maybe complex chemistry could survive the journey. 3I Atlas, if it's as structurally robust as it appears, might represent the kind of object that could make such a journey. Not proof, not even strong evidence, but a proof of concept. Durable interstellar messengers exist. The philosophical value is also significant. 3I Atlas is a piece of another star system. It's matter that formed light years away, under conditions potentially very different from our own solar system. It's a sample of cosmic diversity delivered to our doorstep. Whether it's a weird comet or something more exotic, it's a reminder that the universe still holds surprises. It's a reminder that our models, however sophisticated, are always provisional, always subject to revision when new data arrives. We tend to think of our solar system as the template, the standard against which everything else is measured. We assume that what's true here is true everywhere. But every interstellar visitor is a reality check. It's a data point from a different experiment, a different initial condition, a different outcome. The more of these we collect, the better we understand what's universal and what's contingent, what's fundamental physics and what's local accident. Scientists and space agencies should take note. If another interstellar visitor is detected, we should seriously consider rapid response missions. Not just remote observation, but spacecraft rendezvous. Maybe even sample return. These objects are rare. They're valuable. They're windows into other stellar systems. We shouldn't let them pass by without getting as close as we can. The technology for rapid response missions exists, at least in concept. Small spacecraft with ion drives or solar sails could be pre-positioned in Earth orbit, ready to launch on short notice. If an interstellar object is detected with sufficient lead time, one of these spacecraft could match trajectories, fly alongside the object, and make in situ measurements. Composition, structure, magnetic fields, particle environment, all the things we can't measure from Earth. Sample return would be harder, requiring a high-speed intercept and sample collection mechanism, but it's not impossible. The science return would be immense. 3I Atlas challenges complacency. It reminds us that the cosmos doesn't care about our textbooks. It does what it does, and our job is to observe, measure, hypothesize, test, and revise. Whether this object turns out to be a 1 in a million natural oddball or the first hint of something stranger, it's already served a crucial function. It's made us question. It's made us look closer. And that's what science is supposed to do. 3I Atlas isn't happening in a vacuum. The last couple of years have seen a surge of discoveries and technological advances that are reshaping our understanding of small bodies, comets, and the tools we use to study them. If you want to understand where the field is headed, you need to see 3I Atlas as part of a larger pattern. Things are changing fast. The universe is revealing itself in new ways. And what we learn from this one object might be just the beginning. Let's talk about composition surveys. In the past, studying comet composition meant catching them when they passed close to Earth and hoping you had the right instruments pointed at them at the right time. Now, with the James Webb Space Telescope fully operational and multiple ground-based infrared facilities coming online, we're getting systematic spectroscopic surveys of comets and minor bodies across a wide range of heliocentric distances. Recent observations have revealed unexpected diversity in volatile inventories. Some comets are water-rich. Some are carbon monoxide-rich. Some, like 3I Atlas, are carbon dioxide-rich. This diversity is forcing revisions to models of comet formation and evolution. It's showing us that the simple dirty snowball model is inadequate. Comets are complex, variable, and their chemistry reflects the specific conditions of their formation environment. One particularly interesting recent discovery, reported in a preprint from early 2026, involved a Jupiter family comet that showed spectroscopic signatures consistent with interstellar origin, despite having an orbit that appeared to be bound to the solar system. Follow-up observations suggested this comet might have been captured from interstellar space during a close encounter with Jupiter millions of years ago. If confirmed, it would mean that some objects currently in solar system orbits are actually interstellar refugees, chemically distinct from native solar system bodies. That has implications for how we interpret compositional surveys. It means we can't assume that everything in a solar system orbit formed in that solar system. Now let's talk about observational capabilities. The Punch mission and other heliophysics wide-field imagers are changing the game for detecting and tracking small bodies near the Sun. Traditionally, comets were studied by pointed telescopes, instruments that look at a small patch of sky with high resolution. Wide-field imagers look at large areas of sky simultaneously, trading resolution for coverage. That makes them ideal for detecting fast-moving, transient objects like comets passing through the inner heliosphere. Punch, launched in 2024 and now fully operational, has already detected multiple comets that would have been missed by traditional surveys. Its ability to see faint structures in the solar wind and corona also allows it to study how comets interact with the space environment, tracking tail dynamics and coma evolution in real time. The Stereo mission, despite being decades old, is still delivering valuable data. Its wide-field heliospheric imagers have captured dozens of comets over the years, and the image stacking techniques developed for Stereo are now being applied to other datasets. The ability to combine multiple exposures to reveal faint objects is proving crucial for studying interstellar visitors, which are often faint and fast-moving. 3I Atlas was detected and tracked partly thanks to these techniques, demonstrating the value of long-term missions and clever data processing. There's also exciting progress in automated detection and characterization using machine learning. Astronomical surveys generate enormous amounts of data, far too much for human astronomers to analyze manually. Machine learning algorithms are now being trained to identify comets, asteroids, and other transient objects in survey images, flag unusual features, and even perform preliminary spectroscopic classification. A recent study demonstrated that a neural network trained on historical comet data could identify morphological anomalies, like unusual tail structures or asymmetric comas, with accuracy comparable to human experts. This kind of automated anomaly detection could be crucial for catching rare events like 3I Atlas-style oddities early, allowing for rapid follow-up observations before the object leaves the observable region. Artificial intelligence is also being used to analyze spectroscopic data. Identifying molecular species in comet spectra is traditionally a labor-intensive process, requiring careful comparison with laboratory reference spectra. Machine learning models can now perform this analysis in seconds, identifying molecular features and estimating abundances with uncertainties comparable to traditional methods. This speeds up the analysis pipeline, allowing scientists to make observing decisions in near real time, rather than waiting days or weeks for manual spectroscopic analysis. One speculative but fascinating application of AI in this context is pattern recognition across datasets. Imagine training an algorithm on all available observations of 3I Atlas from multiple telescopes, multiple wavelengths, multiple observation times. The algorithm could potentially identify subtle patterns or correlations that human analysts missed. Maybe there's a periodic variation in jet activity that correlates with rotation. Maybe there's a spectroscopic signature that appears and disappears in a way that suggests compositional layering. Maybe the morphological features evolve in a predictable way that hints at the underlying physical processes. This kind of data mining is still in its infancy, but it holds promise for extracting deeper insights from complex, multidimensional datasets. Looking forward, the question is whether 3i Atlas is an outlier or a harbinger. Are we entering an era where interstellar visitors with unexpected properties become a regular part of the astronomical calendar? The Vera C. Rubin Observatory, once fully operational, is expected to detect 10 to 100 interstellar objects per year, depending on their size distribution and the brightness limits of the survey. If even a small fraction of those objects show anomalies comparable to 3i Atlas, we'll need to rethink our assumptions about what's normal and what's strange. We might also need to rethink our rapid response capabilities. Interstellar objects move fast. They're only observable for weeks or months before they fade into the distance. If we want to study them in detail, we need missions that can be launched quickly, spacecraft that can change trajectories on short notice, and observation campaigns that can be organized globally within days. The technology exists. The challenge is coordination, funding, and the willingness to treat these rare events as scientific priorities rather than curiosities. In 5 to 10 years, will 3i Atlas look like an odd anomaly, a one-off that defied easy explanation but ultimately fit into revised comet models? Or will it look like the first of many, the opening chapter in a new understanding of interstellar object diversity? The answer depends on what we find next, and that depends on whether we're looking, whether we're ready, and whether we're willing to take the strange seriously.